Okay, we finally made it. After all of the given velocity profiles throughout the semester, I'm going to put one together now for you, and it'll involve using both the continuity and the momentum equation. We're going to use those to find the actual velocity profile u of y for flow between a set of parallel plates. So we got this steady flow between parallel plates. We're going to define a coordinate system where in the middle of our thing, so y goes up and down, z goes in another page, x is horizontal. Gravity would act downward, but we're going to neglect it. And we have some boundary conditions that are interesting, right? No slip condition tells us that the velocity at the surfaces is equal to 0. So u and v are both 0 at y is plus minus h. And because this is a 2D horizontal flow, velocity is actually 0 everywhere. Excuse me. The v, the y direction velocity, is 0 everywhere. We want to find u of y. And that's going to happen by putting the continuity and momentum equations together. So let's start with continuity. Which tells us in its most general form that d rho dt plus d rho u dx plus d rho v dy plus d rho w dz is equal to 0. Let's apply as many simplifying assumptions as we can. First off, it's steady, so that gets rid of the time derivative. Second off, wow, that's funny. I never wrote it down. This is an incompressible flow as well. This is an incompressible course, and so it is incompressible. That lets us get rid of the densities. Lastly, it's 2D. And one more thing. We've said that v is 0 everywhere. Well, if the velocity is 0 in the y direction everywhere, then its derivative with respect to y would have to be 0 everywhere, because the derivative of 0 is 0. So that goes away, and what we're left with is just that du by dx is equal to 0. That's as far as we get with that one for now. Doesn't tell us much other than conceptually what this means is that the velocity doesn't change as you move downstream. Let's go ahead and get the momentum equation involved and see if that illuminates anything for us. So we're going to do the momentum, and in particular we're going to do the x direction momentum. So in its most general form, the momentum equation is rho du dt plus u du dx plus v du dy plus w du dz. That's equal to minus dp dx plus rho gx. And we also have to include the shear stress. So that's mu d squared u dx squared plus d squared u dy squared d squared u dz squared. Again, let's apply as many simplifying assumptions as we can. It's steady, so that gets rid of the transient term. The velocity is 0 everywhere, so that gets rid of that term. It's 2D, so we can get rid of this term. We don't have gravity in, well, we're neglecting it everywhere, but we certainly don't have it in the x direction. So no g in the x direction. Again, 2D lets us get rid of this term on this side. Now for the more nuanced one. Continuity tells us that du dx is 0, so that gets rid of this term. And if the first derivative is 0, the second derivative is 0, because the derivative of 0 is 0, and so this also goes away thanks to the continuity equation. And what we're left with is the 0 on the left-hand side, we got rid of everything, is equal to minus dp dx plus mu d squared u dy squared. That's the x direction momentum equation, and we've already used the continuity equation to simplify it. Now for the moment you've been waiting for, we're actually going to solve this to find u as a function of y. So let me move to a fresh page here. I'm just going to take this equation and rewrite it for you. Although I'm going to move it to the other side of the equation of the equal sign. So on the one hand side we get, whoops, wrong color here. I like to be color coordinated. D squared u dy squared, and that has to be equal to a 1 over mu dp dx. I just rearranged the equation from the last step. Now we're going to do a little bit of calculus. Let's integrate this side with respect to y. Let's integrate this side with respect to y. So what's the integral of this with respect to y? Well, just du dy, and that has to be equal to 1 over mu. dp dx isn't a function of y, so that just comes out like so. You can actually just think of dp dx as a constant. We'll get into that later. But we're integrating with respect to y, so a y shows up, and we're going to get a constant of integration that we'll call c1 because we didn't have limits on our integrals. Okay, so let's integrate again. If I integrate the left-hand side with respect to y, integrate the right-hand side with respect to y, that's going to get me now finally on the left-hand side u. Well, that's the thing we're looking for. On the left-hand side, you can see that this is now going to give us a y squared over 2. So we get 1 over 2 mu dp dx times y squared, plus this thing's going to get us c1 times y, and we need a new limit, or a new constant of integration, because we don't have limits on this one either. So that's the general solution. All we need to do is apply our boundary conditions to find our constants. Apply the boundary conditions. So remember, we had fixed plates, which says that u is equal to 0 for y equals plus minus h. You'll notice we have two unknown constants, and so we need two boundary conditions to solve for them. So u is equal to 0, 1 over 2 mu dp dx, when y is equal to h, c1 times h plus c2. So that's applying it at plus h. We can also apply this same condition at minus h as 1 over 2 mu dp dx. Now we're going to do it at minus h. So we've got now two equations, two unknowns. We can solve these. The easiest way to do that is to just add these two equations together, going back to algebra school here for a minute. So the squared's inside here, so that gets away, and so we're just going to get two of those. In other words, the 1 over 2 goes away. So we got 1 over mu dp dx times h squared. The second term, we get a plus h and a minus h when we add those together, so that's a 0. And then the third term here is just going to give us 2c2, just adding these up. And so we can solve that and discover that c2 is equal to minus 1 over 2 mu dp dx times h squared. So that gets us one of our constants. Whoops, pardon that. How badly did I screw things up? Hopefully not too bad. Oh boy. If we have one, we can get the other, because I can take this, sub it right back into here, come on down, and now I have one equation and one unknown. Right, so I can do 0 is equal to 1 over 2 mu dp dx h squared plus c1 times h. Plug in c2 here, you get 1 over 2 mu dp dx h squared. And the beauty of that is that this now cancels with that, which tells us that c1 has to equal 0. So this might not look like much yet. Let me move to a new page to give you the final equation here. I'm just going to take that c1, this c2, sub it into our general solution, and wait till you see what we found. All of that comes together to say that u is equal to 1 over 2 mu dp dx times y squared minus 1 over 2 mu dp dx times h squared. We can simplify this slightly by saying now u is a function of y. Ooh, that got sloppy. Let's try that again. U as a function of y can be written as 1 over 2 mu dp dx times y squared minus h squared. Let's draw ourselves a nice box around that. It might look weird to call this done since there's this term in here, but what's interesting is dp dx is just a number. It's called the pressure gradient, right? This is like delta P per delta X. It's the pressure drop per unit length. In fact, you've seen it before when we did the integral equations. In fact, if you sub them in there, eventually where you'd end up is in the familiar place of P1 minus P2 being for, what was that, tau wall L over D. Remember that whole business? That's the pressure drop, this delta P here, caused by the shear stress. And so it's just a number. So what are we looking at here? Well, it's a thing that depends on viscosity, and as a function of y minus h, a single number, and so this is just a parabolic profile. So there it is. That's the velocity profile between two plates. Quick side note here, what if the top plate moved? Let's let the top plate move at some velocity v. The reason this is interesting is it's the same general solution. The thing that changes are the boundary conditions. So we just have some new boundary conditions to deal with, right? At the top wall, u of y equal to h, the velocity isn't 0 anymore, it's v. So let's evaluate this for some new boundary conditions and see what that gets us, right? What I'm saying is the velocity is equal to v instead of 0 at the top wall, and so we still get the rest of this thing, h squared plus c1 times h plus c2. It's still 0 at the bottom wall. The bottom wall is not moving, so this boundary condition stayed the same. H squared, remember there's minus h squared there, plus c1 times minus h plus c2. Again, we can add these together, and we get now v is equal to 1 over mu times dp dx times h squared, like we did before. This term again goes to 0 and to c2. And so that tells us now c2 is equal to v over 2 minus 1 over 2 mu dp dx times h squared. And if I take this, substitute it back in, I can get the second constant of integration to be 0 equals 1 over 2 mu dp dx h squared plus c1 times minus h v over, oops, sorry, that's v over 2, not v2. I'm just going to sub this in. V over 2 minus 1 over 2 mu dp dx times h squared. Again, this thing cancels with that thing, and we're left now, C1 isn't 0 anymore. C1 now is V over 2H. And you're about to see something really interesting happen when I put all this together on the next page. So let's bring this in for a landing. We found our constants of integration by substituting our known boundary conditions. And it gave us all of this. Which I can simplify slightly to give me u of y equals 1 over 2 mu dp dx y squared minus h squared. So you saw that part from the last solution, but what we're going to add to it now is the velocity of the top plate, v over 2, y over h plus 1. And you might be saying, yeah, whoop-de-doo. What does that tell us that we've should have seen before? And the answer is, how about if I don't apply a pressure gradient? If I don't have an applied pressure gradient, that means that this term's gone, and we're left with, because I'm saying that dp dx is equal to 0 if I don't apply a pressure gradient, where that leaves us is that all this is gone, and you're back to u equals v over 2 times y over h plus 1. That's just the linear profile that we've been looking at all semester, with a coordinate shift where y equals 0 is at the center. And so that's actually the linear profile that we've been looking at all semester. This is where it comes from. All right, so just to summarize, what the heck did we just do? What we just did was we applied the conservation of mass and the conservation of momentum to our system. We canceled out everything that we could possibly cancel out, and it left us with this single differential equation to solve. That differential equation, we substituted in we integrated twice, and then we applied boundary conditions to find the constants of integration. And those constants of integration are just real things, and that leaves us with a final solution that looks like this, where we have some applied pressure gradient, and we can now find the velocity as a function of position.